Hello guys, in the last video we saw how to solve the Schrodinger equation for the harmonic oscillator potential. It was the algebraic method, and this is part 2, the analytic method. Let's get right into it. We return now to the Schrodinger equation for the harmonic oscillator. So here they restate the Schrodinger equation, time independence with the harmonic oscillator potential. And we solve it directly by the power series method. Things look a little cleaner if we introduce the dimensionless variable xi. I think this is called xi. So this is a collection of variables here. If you plug that into there, simplify things, we get the Schrodinger equation in terms of xi, right? Because we have dx here, but xi is in terms of x. So we find d xi, and we replace everything, and it looks like this, where k is the energy in units of 1/2 h bar omega. So this is also another unit. So we introduce xi and capital K, replace things here, move things around, and we get this more simplified looking equation. Second order differential equation with respect to xi of the wave function, and here we have the wave function with some constants in the front. Our problem is to solve equation 2.37 and in the process obtain the allowed values of k and hence E, because k depends on E. So we want to find the energies and the wave functions. But we found the wave functions previously. This is just going to spit out the wave functions in a different method. To begin with, note that at very large E, which is to say at very large x, I just call this thing E. I might mix it up a little, xi, epsilon E, whatever, let's just call it E. E squared completely dominates over the constant k. So in this regime, you can approximate this equation as this one here. So what they're saying is, let's look very, very far where this E is very big. If this E is very big, a very big number minus like a super regular size number, it's just going to equal basically that very big number. So it's almost like you can completely disregard or neglect this minus k, and that's what they're doing here. So it's an approximation, that's why they have this approximation equal sign, which has the approximate solution. Check it. So plug this into this equation, see if this is accurate. This differential equation spits out solutions that are these, and they also have the approximate sign here because we're approximating here. The b term is clearly not normalizable here. It blows up as x goes to infinity. So this is not normalizable because as x or e goes to infinity, this e to the power of xi squared over 2 goes to infinity as well. But this one, e to the power of negative xi squared over 2, this goes to 0. Because if you plug infinity into here, it's like a decaying function, so this e goes to 0. But this one goes to infinity. It blows up, so we don't like this. The physically acceptable solutions then have the asymptotic form, boom. So we just keep this thing here, and he puts brackets over here because we need to find what function fits inside these brackets. There's also this a term which he just absorbs into these brackets. This suggests that we peel off the exponential part. So we have this solution here, where there is a function of xi. Inside there he calls it h, in the hopes that what remains, h of xi, has a simpler functional form than psi of xi itself. Differentiating equation 2.78, this one, gives us this, so the derivative of this gives us this, derivative of h with respect to xi, and then this minus xi times h. Where does this come from? Is this the... Where does this minus xi h come from? I'm not sure actually. Take a derivative of this. Oh, it's because it's a product, so you do product rule. Multiply by this, then derivative of this, and the derivative of this spits out a xi, and then derivative of this here multiplied by this. So this is the product rule over here. Nice. And the product rule has a minus sign in front of it because there's a minus sign here which gets pulled out when you take this derivative. Alright, now take the derivative again and we get this. Basically we take two derivatives because we're trying to build up this equation here, and it has the second derivative with respect to xi. Second derivative with respect to xi. We just take the solution, differentiate twice, and we get this. So the Schrodinger equation 2.73, which we saw over here, the full Schrodinger equation, now we bring back the k because this approximation was just to see what happens at the ends of the wave function. It looks like this. So we have second derivative with respect to h, right? Because what we had here, psi, now was replaced by this h thing and this other stuff here. So now we have a Schrodinger equation just with respect to h, and the h is what we're looking for. Boom, second order derivative, first order derivative, which comes from here. This k minus 1h, this is here as well, and this equals 0. Why does it equal 0? Okay, we're going to skip that. I propose to look for solutions to equation 2.79 in the form of power series in xi. So we're going to expand this function h of xi in terms of a power series, right? This is like a kind of like a Taylor series, maybe. So this infinite summation exactly equals the unknown function h, differentiating the series term by term. So we're going to differentiate once this h, which we approximate or we expand it in the form of a power series. We differentiate this once to get this derivative here, and then we differentiate again to get this derivative here. And over here there's an h, so we could just plug this whole thing here into this h. So we take the first derivative, you literally just take derivatives, so derivative of a constant equals 0, derivative of a1 xi is equal to a1, derivative of a2 xi squared is equal to 2a2 xi, and so on and so forth. Here is the series version. This is just like the term version. And the second derivative, again, just take a derivative. Derivative of this gives you this. Putting these into equation 2.8. I think this is actually a mistake. Check this out. Putting these into equation 2.8, we find, so he's not actually putting it in equation 2.8, because 2.8 is the first h. He meant to say putting these into equation 2.79. All right, so Griffiths, in the 4th edition, please correct this, my boy. Looks good though. We basically replace everything here. We replace the second derivative with this second derivative sum, and you can see all of these have the sum j from 0 to infinity. So instead of writing it 3 times, he pulls it out to the front. Here is the first term, j plus 1, j plus 2, a subscript j plus 2 times psi to the power of j. And the psi to the power of j also is everywhere here. They just move it to the front. But also keep in mind here we have psi of j, here we have psi of j minus 1 psi of j. So some little work had to be done for this psi of j minus 1 to be fixed a little bit. And I think that work is over here. So here there is a 2j a subscript j instead of a j. So maybe this 2 pulls out something from here, and this reduces to xi of j instead of xi of j minus 1. Doesn't matter too much. We're just seeing the process of how he's doing this. It follows from the uniqueness of power series expansions that the coefficients of each power of xi must vanish. Okay. So what does that mean? It looks like he just takes this whole thing inside the brackets and he equates that to 0. Interesting. Well, this whole equation equals 0, and this equals 0 actually was confusing to me. I don't know where this came from. I'm assuming once you plug things in, you move stuff around, this just equals 0 on the other side. But still kind of weird. You might want to ask yourself, where does the 0 come from? But take a look at this. Here we have a product. Inside we have this this thing which depends on j, and all of that is being multiplied by this xi of j here, which also depends on j. So this equals 0. That means either this can equal 0 or everything inside can equal 0. Right? So he says, okay, let's check if everything inside equals 0, what happens then? And we get this equation here. So this is still the Schrodinger equation. We just did so many manipulations. But keep in mind what this means. We expanded the h function here in terms of a series, and we got in a series you have these terms here, the things that you add over, j equals 0, j equals 1, j equals 2, all the way to infinity. So they are here. We also have these aj's, which are the coefficients inside of the series. We also have this k, which is the energy, which is what we're looking for. And that's it. Let's keep going. And hence that aj plus 1, which is, or aj plus 2 here, is solved. So you isolate for aj plus 2 and you get this. It is, what the heck, this thing can't, okay, I maybe click too much. This thing can't disappear here. So this aj plus 2 is in terms of aj plus 1. So if you have, or sorry, not plus 1, aj. If you have aj, you can fabricate aj plus 2 using all of this here and the energy. Its recursion formula is entirely equivalent to Schrodinger's equation. Starting with a0, it generates all the even numbered coefficients. So with a0, you plug it into here, you get 2. You have 2, you plug it in here, you get 4. You have 4, you plug it in here and you get 6, and so on. And if you start with a1, you get A3. If you start with A3, you get 5, and then so on and so forth. So this equation here gives you the solutions to the Schrodinger equation because, boom, check this out. Here you have A1, here you have A0, A1, A2, and so on, and then this is the Schrodinger equation in terms of this function. So if we know these coefficients, then we know h, and if we know h, we basically know how the entire Schrodinger equation works here. A little bit strange, a little bit weird, but this is the power series expansion. Cool. Let's check. We read the complete solution as h of xi is equal to h subscript even of xi plus h subscript odd of xi, where h even is equal to this and h odd is equal to that, is an odd function built on A1. So it's built on A1 and this one's built on A0. Kind of interesting. Thus, equation 2.82 determines, this one here, determines h of xi in terms of two arbitrary constants, A0 and A1. If you have A0 and A1, you can fabricate A2, 3, 4, 5, all of the other ones, which is just what we would expect for a second order differential equation. Second order differential equation depends on two constants. Cool. However, not all the solutions so obtained are normalizable. For at very large J, the recursion formula becomes approximately, so very large J, boom, 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 because the series goes from J equals 0 all the way to infinity. So at very large J, he says this recursion formula simplifies to this. And with the approximate solution, a subscript j is approximately equal to c, some constant, over j over 2 factorial for some constant c, and this yields at large xi, where the higher powers dominates, this e to the xi squared, and this thing blows up to infinity. Now, if h goes like exponential, so if h is proportional to e to the power of xi squared, then psi, remember psi, that's what we're trying to calculate, goes like e to the power of xi squared over 2, equation 2.78, which is precisely the asymptotic behavior we didn't want. There is only one way to wiggle out of this. For normalizable solutions, the power series must terminate. There must occur some highest j, call it n, such that the recursion formula spits out an plus 2 equals 0. This will truncate either the series h even or the series h odd. The other one must be 0 from the start. A1 equals 0 if n is even, or A0 is equal to 0 if n is odd. For physically acceptable solutions, then equation 2.82 requires that, equation 2.82, this one here, it requires that k is equal to 2n plus 1. So basically what he's saying is, this equation, if we look at very large j's, something like this happens and the solutions are not normalizable. So in order to force normalization, one of these A1s or A0s have to be 0, and also at a certain distance, so at a certain j, like j equals 0, 1, 2, at a very large number j, call it n, all further j's will yield aj's of 0. Okay, if that makes sense? So because of this kind of deducing logic, in mathematics, it doesn't matter if things blow up. So if you're trying to solve this mathematically, just an arbitrary kind of differential equation, you don't care about infinities. But in quantum mechanics, we don't like infinities because that leads to non-normalizable wave functions, which is not realistic. A real system can only be described by a normalizable wave function, which means the wave function cannot blow up or turn to infinity at the endpoints. So because of this, we get this condition here. K is equal to 2n plus 1, which looks very similar to the energies from the harmonic oscillator. From the previous section, the raising lowering operators. For some positive integer n, which is to say, referring to equation 2.74, that the energy must be boom. So we replace k with what we saw k was before when we introduced k here. It has a 2, it has an e, it has an h bar omega. And then we pull out the energies of the harmonic oscillator, which we saw were the same ones from the raising lowering operators. Thus, we recover by completely different method the fundamental quantization condition we found algebraically in equation 2.62 in my previous video. It seems, at first, rather surprising that the quantization of energy should emerge from a technical detail in the power series solutions to the Schrodinger equation. But let's look at it from a different perspective. Equation 2.71 has solutions. Let's see 2.71, what is it? 2.71, this one, the original Schrodinger equation. Equation 2.71 has solutions, of course, for any value of e. In fact, it has two linearly independent solutions for every e. But almost all of these solutions blow up exponentially at large x, and hence are not normalizable. Imagine, for example, using an e that is slightly less than one of the allowed values, say 0.49 h bar omega, and plotting the solution, figure 2.6a. That's what it would look like here. Now try an e that is slightly larger, say 0.51 h bar omega. The tail blows up in the other direction here. So what they're plotting is the wave function here. As you tweak the parameter in tiny increments from 0.49 to 0.51, the graph flips over at precisely the value 0.5. Only here does the solution escape the exponential asymptotic growth that renders it physically unacceptable. So this is really cool. So as you tweak the energy, the wave function right here in the middle looks good, and then here at the ends, at the extremities, boom, it blows up to infinity. At the other extreme, boom, it blows up at infinity. If you tweak the energy again, the wave function in the middle looks pretty much the same, and then at the extremities, boom, it blows up to infinity again, boom, it blows up to infinity. So as you tweak the wave function, let's say you plot this on a computer, you see the wave function explodes at the infinities, you tweak it again, maybe it explodes less far, and then at some point, boom, it flips and it explodes the opposite way. So right kind of between this range, between the range of 0.49 h bar omega, 0.51 h bar omega, is the proper solution where these explosions don't happen. The wave function just nicely, delicately touches zero all the way to infinity, and that is a normalizable solution. Like I said before, in mathematics, this is a solution and this is a solution, but in physics, this is not a real solution. It doesn't describe a real particle because we need the wave function to be normalizable. That's why we started talking about normalization in chapter 1. It's super important. Table 2.1, the first Hermite polynomials h of n, boom. Actually, where are the Hermite polynomials? They're not even talked about yet, so this is just a figure that's going to be introduced a bit later. For the allowed values of k, the recursion formula reads, boom, if n equals 0, there is only one term in the series. We must pick a1 equals 0 to kill h odd, and j equals 0 in equation 2.85 here yields a2 equals 0. So, maybe this is a bit confusing, maybe we're not understanding this too in depth, but we're just going to keep reading to see like what the final answer is. This is just a strategy to get the solutions. H subscript 0 of xi equals a1 or a0, and hence psi of 0 of xi is equal to a0 e to the power of negative xi squared over 2, which apart from the normalization reproduces equation 2.60. For n equals 1, we take a0 equals 0, and equation 2.85 with j equals 1 yields a3 is equal to 0. So h1 of xi is equal to a1 xi, and hence psi1 xi is equal to a1 xi e to the power of minus xi squared over 2. Confirm equation 2.46 for n equals 2, j equals 0 yields a2 equals minus 2 a0, and j equals 2 gives a4 equals 0. So, okay, I guess I see what's going on here. We expanded h in terms of a power series, but psi, we don't want it to be an infinite power series, we want it to just be one function. So he's arguing here that there has to be something here that equals 0. Why is this argument happening? I honestly don't know, but I don't think it's too important to really solidify this. If you want to understand it more in depth, maybe we should read through this again or do some of the problems. But right now we're just going to zoom through the theory. H2 gives you this, and Xi2 or Psi2 gives you this, and so on. Compare problem 2.10, where this last result was obtained by algebraic means. So this we obtained in the raising and lowering operators in problem 2.10. I haven't done it. We might do it in the future. In general, h subscript n of xi will be a polynomial of degree n in xi, involving even powers only if n is an even integer, and odd powers only if n is an odd integer. Apart from the overall factor a0 and a1, they are the so-called Hermite polynomials, capital H subscript n of xi. So we found out that these things can be described by this completely other function, Hermite polynomials, which mathematicians have discovered somewhere else working with differential equations. The first few of these are listed in table 2.1 right here. So h of 0 is 1, h of 1 is e to the xi. Notice that xi is to the power of 1 here. So each odd term, so xi3 or h subscript 3 gives you xi cubed minus xi. But h subscript 2 gives you psi squared. So everything with a 2 or an even number gives you even power polynomials. Everything with a 3 gives you odd power, or 3 with an odd number. 3 or an odd number gives you odd number polynomials, and this is the Hermite polynomials. In terms of xi, you can replace xi with x here. Since we use x for position in quantum mechanics, they use a different variable xi. I think it's a confusing variable, but it doesn't matter. It's also hard to write. The first few of them are listed in table 2.1. By tradition, the arbitrary multiplicative factor is chosen so that the coefficient of the highest power of xi is 2 to the n. With this convention, the normalized stationary states for the harmonic oscillator are, boom, and we get the solution. How do we get this? Pretty big leaps. Normalization constant is here. This factor, 2 to the n, comes from here. And then the Hermite polynomials, and then e to the... Actually, this e to the minus xi squared over 2 we got from the previous, in the beginning when we made that approximation looking at very large xi's. And we were looking for this, and we just found this. So expand in power series, do a bunch of simplifications. You find out that the power series solution actually gives you these functions that have already been discovered before. And then we got the normalization factor, and we got some other stuff coming out from the Hermite polynomial. They are identical, of course, to the ones we obtained algebraically in equation 2.68. So here are the solutions to the Schrodinger equation with the harmonic oscillator potential using the analytic method or a power series expansion. Pretty interesting, but pretty difficult to do. In figure 2.7a, I have plotted psi subscript n of x for the first few n's. So that is here. The quantum oscillator is strikingly different from its classical counterpart. Not only are the energies quantized, but the position distributions have some bizarre features. For instance, the probability of finding the particle outside the classically allowed range, that is with x greater than the classical amplitude, for the energy in question is not zero. See problem 2.14 here. And in all odd states, the probability of finding the particle at the center is zero. Only at large n do we begin to see some resemblance for the classical case. In figure 2.7b, this one here, I have superimposed the classical position distribution, problem 1.1, on the quantum one for n equals 60. If you smoothed out the bumps, the two would fit pretty well. So take a look at this. First of all, the stationary states, the wave functions describing the solutions to the Schrodinger equation with the harmonic oscillator potential, yield these ones for different n's. So this is n equals 1? Is it 1 or 0? I think it starts at 0 in this case. For the particle in the box, it started at 1. But in our case, k of n, k here, which is the energy, this one starts at 0. So if you plug 0 in here, you get the ground state energy, which is 0, 0 plus 1 half, 1 half, 1 half h bar omega. So the ground state energy here, the 0th wave function, is the h bar omega, 1 half h bar omega energy particle that lives in the harmonic oscillator potential. You increase by 1, add a raising operator, or use the Hermite polynomial subscript 1. You get this, boom. You raise it again, you get this, boom. All of the energies are quantized, as we saw with the raising lowering operators. And it is an interesting, let's check the probability distribution. So this is just xi. If you absolute value square this, you get the probability distribution of finding the particle. So let's say I have ground state particle in the harmonic oscillator. I take a measurement. I am most likely to find it in the center. But if I have the first excited state, so raising operator once on the ground state, we get this. The probability of finding the particle in the center of the well is 0. Same thing for the n equals 3. Very, very interesting. And also, there is some non-zero probability of finding the particle outside the harmonic oscillator well, which does not happen in classical mechanics. So here you can see this dotted line on the bottom is the superimposed classical potential, and here we have the 60th stationary state. It does all this crazy stuff. Imagine, expanding this a lot, and it looks like it matches just a little. I mean, yeah, it looks like it's getting there. So as you increase size, you get more and more excited states. It more closely matches the classical limits, but at lower limits here, you can see some quantum behavior. Okay, what does all this mean? Let's check. We got some problems. and that is the chapter. So I went through this pretty quickly. Like I said, it's kind of strange, but here we have 3 problems. We also didn't have an example in this chapter or in this section. So it's a little bit weird how you would be able to use this stuff. But here we got some problems. We could do these if you guys want. Don't feel stressed if you don't understand this. You should just read it and absorb the general essence of what's happening. So here's the general essence that I understand. The harmonic oscillator has a specific potential. We plug this into the time-independent Schrodinger equation and we try to solve it. There are 2 ways that are generally used to solve it. Either we expand the psi, the wave function that we're trying to solve for, in terms of a power series. This is the analytic method, and we get solutions in terms of these Hermite polynomials. So here is the solution. The way to get the solution is a bit crazy, but the actual solution is pretty important. So Hermite polynomials right here. Another way of doing it is the algebraic method. You factor the Hamiltonian into 2 things, which we will call the raising operator and the lowering operator. And through some arguments, you can also get the solutions here, and you get them in terms of raising and lowering operators. So you have the ground state psi. Basically, you plug in 0 here, you get 0 for the Hermite polynomial. The 0th Hermite polynomial is just 1, and then you simplify a bunch of things here. So all of this gets removed. 2 to the power of 0 is 1, 0 factorial is 1, 1 over 1 is 1. So basically, this whole thing gets removed. So the ground state wave function looks like this exponential, this Gaussian exponential, and a normalization factor in the front. If you apply the raising operator, you can get the excited states and you can get the excited state energies. So 2 different methods of solving this. As you saw, it was much more difficult than the infinite square well. The infinite square well we were able to solve because we learned in physics how to solve differential equations, and differential equations that have solutions as sines and cosines you have seen in class before. But solving differential equations with the harmonic oscillator potential, especially for the Schrodinger equation, as you saw, it gets pretty intense. You have to use a series expansion, or you have to use some crazy raising lowering operators. I would say that the way of solving this is not too important. The mechanics of what's happening is important. So you look at this and you're like, what is happening here? Do I understand this as a solution? Does this make sense to me? What is this Hn here? If you could look at this equation and describe every component inside of it and describe what this psi of n means, then I think you should be good. All right. So thank you guys for watching. In the next video, we're going to check the next potential. As you can see, there's a pattern in chapter 2. We have the free particle. In each chapter, there is a new system with a new potential, and we put that potential in the Schrodinger equation and we grind it forward to try to get a solution, and the solutions give us something interesting. We haven't talked about the solutions too much, what those interesting things about the solutions are, because we have to do the problems, but for me, I like reading a lot first and then we can do some problems. Hopefully that will be pretty fun. Thank you guys for watching as always. See you in the next video, section 2.4, the free particle. Peace out, guys.